All right. So question 1 is asking how many oxygen atoms does 400 milliliters solution of 5 molar aluminum sulfate contain? Okay, so we're given molarity, and molarity, the equation for molarity is, what is that equation?
M equals N over V.
N over V, yeah, yeah. N is moles, so I'm just gonna say moles over liters. It's moles divided by volume, volume is in liters. So. And it's asking for the number of oxygen atoms, right? So we know we should probably eventually get to moles of oxygen atoms. And if we know the moles of oxygen atoms, then using a special number called Avogadro's number, we can find the amount of oxygen atoms. But how do we find moles of oxygen atoms to begin with? So we can find the moles of aluminum sulfate. And if we know how many moles of aluminum sulfate there are, do we know how many moles of oxygen atoms there are? Yeah. So we're going to do 0.4 times 5, 0.4 liters times 5 molar is going to be the moles of aluminum sulfate. And what do you get when you put that into the 2? Oh yeah, that sounds right. So 2 moles of Al2SO4. And what's the ratio of moles of aluminum sulfate to moles of oxygen atoms?
Well,
You all agree with this guy? This guy, Nick? For every 1 mole of aluminum sulfate, there's 12 moles of oxygen, right? Because you have to distribute that 3 in there. So 12 moles of oxygen. And we know that this is where we use that special number. So for every 1 mole of oxygen, there's 6.022 times 10 to the 23rd oxygen atoms. And if you put this into the calculator, what did y'all get?
it sounds nothing like
Wait, what's that?
I think I'm wrong. I got 1.45 times 10 to the 25th.
1.45 times 10 to the 25th.
That sounds about right.
Did y'all get the same answer? Okay, cool. So are there any questions on number 1? We're all good on number 1? So the only new thing about this problem was using the molarity equation, because other than that, it's just basic stoichiometry of moles of one thing converting to moles of another thing, converting to atoms using Avogadro's number. So the only new part that might be new to y'all maybe is finding the moles using that equation for molarity at the beginning. All right, number 2, what mass and gram? Oh, you got this one, Rich.
Of course, this guy rolled to me on the number 2 problem. All right. What mass in grams calcium nitrate is required to produce 350 milliliters of 0.085 molar solution? This is kind of like the first problem, right? Kind of, sort of. Yeah.
First part.
Yeah, I mean, for the most part, we do the same steps. So we need to get to grams. So to get to grams, we have to get to moles at some point. How can we get to moles using the information we're given here?
0.085 times 0.35.
Yeah, if we multiply the molarity and the volume together. So converting the milliliters to liters, all that jazz. What do you get when you did that?
0.02975.
0.02975. This is moles, calcium nitrate. What's the formula again for calcium nitrate? Yeah, it's CaNO3 2. And how do we get from moles to grams now?
Like molar, right? Multiply the molar mass.
Multiply by the molar mass. So what is the molar mass of calcium nitrate?
Yeah, plus 2, right?
Goes to anybody?
64.08.
164.08 grams. All right, now when you solve this out, what do you get?
3 oxygens per nitrate.
4.88, just standard.
4.88. On the dot, no more decimals, 4.88. All right, 4.88 grams of calcium nitrate. All right. Let's say I wanted to use some advanced jargon, right? Let's say I cared about sig figs. How many sig figs should I have in this number? All right. Raise your hand if you think it's 3. High with pride. Raise your hand if you think it's 4. Correct answer is actually 3. Because if we look here, right, the 0, you go on whatever's least in the problem. So we have 350.0. Because of the 0.0 here, this 0 is significant. So there's 4 sig figs in that number. And then if we do the 0.085, we can see that there's 3 sig figs here. So there's 3 here. So our final answer should have 3 significant figures, which it does with 4.88 grams. Any questions on that? Right. Number 3. Determine whether the following compounds are soluble in water. All right. David, for A, lead 4 bromide, soluble or insoluble? Is indeed insoluble.
Lead's always insoluble, right?
Not necessarily.
Why is the exception, right? Forgot.
Or lead is a common exception for stuff that is soluble or insoluble. So in this case, bromine is usually always soluble, but lead is one of the exceptions. So lead is indeed insoluble. But sometimes I'll be kidding. Sometimes I do stuff without the knowledge of other stuff. So what charge does lead have in this?
4 plus 4 plus.
How,
Well,
or in what instance is lead insoluble? Or yeah, it's 2 plus. So since this is lead 4 and lead 2, can we make, or not lead 2, can we make the generalization that lead 4 is going to be insoluble? To put it in simpler terms, lead 2 is the one you see on the solubility chart, right?
Yeah.
So can you make, since this isn't lead 2, can you say that, can you make the same exception? Can you make the same rule? No, right? So because, all right, remember this. If you get nothing of what I'm saying, remember this. It's lead 2 plus, that's an exception, not lead 4 plus. So if you have lead 4 plus, then this is actually soluble. Because bromine is normally soluble and lead 4 isn't an exception. So it's important to not only pay attention to the metal you have, but also the charge of the metal if there are multiple charges. Does that make sense to everybody? All right, let's try this next one. It's a bit easier. Calcium sulfate, soluble or insoluble?
That was insoluble.
Insoluble.
I thought it was calcium 2 plus wax.
What is sulfate normally? Soluble or insoluble? It's actually soluble. So it's soluble, and is calcium one of the exceptions? It is, right? The Castro barium. So calcium, strontium, and barium. So this actually is getting an insoluble.
It doesn't matter if it's calcium 2+. Or
Calcium can
it
only
is
have
just-
one charge.
Yeah,
So
that's
it's always.
Okay, that's fine.
It's only those like transition metals you have to watch out for once the charges.
Oh. Oh, no, sorry. I was just searching.
All right. Ammonium hydroxide, soluble or insoluble?
Soluble.
This one is soluble. Yeah, ammonium, always soluble. Burn it into your mind. Take a, I don't know, what do people do? Like brand it into their brains a little, well, don't physically brand yourself, but like, you know, brand it mentally. So ammonium is always soluble.
Brand myself, gotta do it now.
That's a reverse psychology, so you don't actually.
Oh, you just told me not to afterwards, so.
Uh,
It cancels out.
do what you want, I can't control you, but ammonium hydroxide, point being, ammonium is always soluble. All right. Mercury or HgCl2. Something with mercury.
Soluble?
Yeah, because chlorine is always.
David shaking his head. Why are you shaking your head?
Because mercury is one of the exceptions. It's H2+, right?
Yes, the thing you'll see on the chart is Hg2 2+. Or is it just Hg?
No, it's Hg2 2+, which makes it insoluble.
All right, Hg2 2+. This is actually the thing you'll see on the chart. So since this is the thing you see on the chart, chlorine, normally soluble, mercury is one of your exceptions, insoluble. This gets a big fat insoluble right here.
Dimer. That's mercury 1, this is mercury 2.
All right, so another important lesson, always look at your solubility chart. Okay, no, nobody cares, but anyways, the thing on the chart is Hg2 2+. So if you look at the thing on the chart, does this mercury have a 2 next to it? Or this one in the problem? No, so can we say that this thing is insoluble? So this actually is soluble.
Yeah, so the exception for chlorides and bromides and iodides is when it's bonded to mercury with the +1 charge. So in this case over here, we have 2 mercuries, right? Because that subscript tells us how many atoms we have, right? So we have 2 mercuries, each one with the +1 charge. And these form what's called a dimer. So you get Hg2 2+, but in reality, it's mercury with a +1 charge. So we call it mercury 1. Mercury 1 will make chlorides, bromides, and iodides insoluble. Okay, mercury 1 will make chlorides, bromides, and iodides insoluble. But what we're dealing with here is Hg2+, mercury with the +2 charge. So this is mercury 2. Mercury 2 is not going to make chlorides, bromides, iodides insoluble, all right? So it's important to know that HgCl2, this one here in the problem, is going to be soluble, but if you saw Hg2Cl2, that would be insoluble because that's going to be your mercury with the +1 charge. So it's important when you're looking at mercury, it has to be the mercury with the +1 charge, which is seen as Hg2 2+, okay? So that's why D is actually soluble because it's not the exception. It's mercury with the +2 charge, not mercury with the +1 charge. Does that make sense? Okay.
All right, point being, don't do what I did on problems A and D and look at your chart closely.
My rules actually said 2 plus is the exception, and I just looked it up, and it says 2 plus is the exception.
So it says HG 2+ on there. Yeah, that's the thing too, like different charts say different things.
Yeah, I mean, the chart I'm looking at and the one that I tell everyone to study is HG 2+ as the exception. I can check with the professor to make sure.
That's what I said actually, but isn't that, are you saying that is HG plus or HG 2 plus?
The one in D is HG 2+.
So that means it is insoluble, right?
It's soluble, not, it's not a mercury 1. Because mercury 1, you have 2 mercuries, each one with a +1 charge, overall charge is +2. So don't get that confused, that +2 charge confused with the actual charge of each mercury.
Okay, so then what's the charge of that one then?
Yeah, so let me get some blank space over here. So the one that we're dealing with right now is HgCl2. This is going to have a mercury of Hg with a +2 charge and Cl-, right? So when you do your crisscross, you get HgCl2. If you had been dealing with the dimer I was telling you about, which has an overall charge of +2, but each mercury is a +1. So we're dealing with mercury 1 with Cl-, then you would get Hg2Cl2. That would be insoluble.
So for that one, you're saying 1 mercury would have a charge of +1, I mean 1 plus.
So this one I'm saying, it has 2 mercury atoms with a +1 charge on each one. Overall charge would be +2
And so is the exception referring to the overall charge or per mercury?
per mercury. So mercury 1 comes, it forms a dimer. Okay, so you're only gonna find mercury 1 as Hg2 2+.
Okay, now I get it. So, and the exception says Hg2 2 plus is the exception.
Exactly, so
not just
it's
HG.
talking about mercury 1.
Okay, gotcha.
Yeah, okay, so it's mercury 1, okay, that's the exception. You just, when you look at it, you might see the +2 charge, you might get that mixed up with mercury +2, but it's actually 2 mercury 1s dimerized together, okay?
Point being, there's a difference between this one. So Hg 2+ and then Hg 2+. Or no, always look at what is on your chart. All right, this is a more easier one. Barium hydroxide. Soluble or insoluble? Is indeed soluble. Because what is hydroxide normally? Insoluble. What is your exception? Yep, group 1 and heavier group 2, barium hydroxide. All right. Have y'all learned this yet? Barium hydroxide is a strong what?
Base.
Yeah, strong base. So barium hydroxide, strong base. Strong base means it completely separates. So barium hydroxide is soluble. All right. Cesium phosphate, soluble or insoluble? All right, who agrees and says insoluble? Who says soluble? Solubles, 1. It is soluble. Because if you look at your periodic table, cesium is actually a group 1 element. It's the last one on group 1. Double check me if you want, atomic number 55. But cesium is, point being, cesium is in group 1. And if you remember, group 1 metals are always what? Yep, group 1 is always soluble. All right. We have tungsten nitrite, or tungsten 3 nitrite. All right. Soluble or insoluble? What are we thinking?
It's only nitrates, not nitrites.
Nitrates, not nitrites.
And that's a nitrite though, right?
It is indeed a nitrite.
I'm gonna say insoluble.
All right, insoluble. All right. Who thinks it's soluble? Show of hands. This thing can dissolve in water 100%. If you slap a cube of tungsten 3 nitrite in water, it will dissolve. All right, raise your hand if you think it's insoluble. There is no way in HE double hockey sticks that if I put tungsten 3 nitrite in water, it'll dissolve. And I'm with the second group on this. I personally would say that it is insoluble. Because, right, I see this and I go, okay, tungsten, I've never seen that before in any of my exceptions to make something soluble, so it has to be insoluble. That is my general format of that. But what if I did some magic manipulation and this was instead WNO3 3? What would this be now?
Yeah, then it'd be soluble.
Then it'll be soluble, right? Because it's nitrate. The important thing, check your polyatomic ions too. All right. Last one. Soluble or insoluble? Insoluble. Right? Look very closely at what the charge is on that copper. Look very closely.
Copper 2 is not the exception, is it? Trying to remember. Actually, wait, I think it is the exception. It's like 8, it's like 2, it's like a +2. Calcium 2 plus.
I would have taken off.
I think copper is no actually. I don't know. No, it doesn't make sense.
All right. Final verdict. Soluble or insoluble? All right. Be going with insoluble on this one. Is that what the general consensus believes? General consensus is correct. This is insoluble. Or is it? Or is it? Yeah, it's insoluble. Point being, copper 1 is the exception on the chart. Copper 2 is not. Right. On to this stuff.
All right, so I'm gonna do a little brief, hopefully quick lecture. So this is strong electrolytes. We're gonna talk about strong, weak, and non-electrolytes really quick so we can go on to problem number 4. So strong electrolytes are something that 100% dissociate in water. So I'm gonna use some abbreviations here so I don't misspell things, and so that way I can save some time. In water. So strong electrolytes, there's 3 classes of strong electrolytes. There's strong acids, and we're going to abbreviate strong acids by SA. And there's 6 strong acids that you need to know about, okay? So strong, do y'all know them? So hydrochloric acid's one of them. Acetate is a very weak acid, so no. HBr, I heard. Hydroiodic acid. Sulfuric acid. Perchloric acid, there we go. So HClO4, and then there is one more. HMNO4? HMNO4? No, that's probably a really weak acid. It's nitric acid, there we go. All right, those are the 6 strong acids. Later, we're going to talk about weak electrolytes, which includes weak acids and weak bases. How do you know if something's a weak acid? It's not one of the 6 strong acids, okay? So every other acid that's not in this list is a weak acid. Strong bases. These include things, mainly in this class, we're going to see hydroxides, okay? So soluble hydroxides, anything that is going to make a hydroxide soluble. So, oops. So we see group 1 is always soluble, right? So group 1 hydroxides. So that would be like sodium hydroxide, lithium hydroxide, potassium, cesium, all that good stuff, okay? So group 1. We know calcium, strontium, barium, Castro-Bear, right? Those will make soluble hydroxides. And then we have. Last one is going to be ammonium. Ammonium makes things soluble. So ammonium NH4 plus is going to make a hydroxide soluble. So if these are attached, if these are the cations, group 1 calcium, strontium, barium, or ammonium, and your anion is hydroxide, it's going to be a strong base, okay? So OH minus. So when it's paired with hydroxide, we all get that? These are all memorization things. This is how you're gonna know if something's strong or weak. And then the last one is soluble salts. So again, this is anything that will, this is just comes down to solubility rules. If it dissolves in water, it's a strong electrolyte. If it's an exception, so if it's something that's insoluble, it's what we're gonna call later a non-electrolyte because it's insoluble. It doesn't dissociate into ions. All right, so weak electrolytes. These dissociate in water around 5% of the time. So 5% dissociation rate. All right, so again, these are things that are going to be weak bases and weak acids. So I'm not going to list out every weak acid because there's thousands of them. But if it's not one of those 6 strong acids, it's automatically a weak acid. Do we get that? So that's how you're going to be able to determine if it's a weak acid. Is it? You ask yourself, is it one of those 6? Answer is no, then it's a weak acid, which means it's a weak electrolyte. So abbreviated WA to save some time. And then weak bases. This is going to be stuff typically organic compounds. So something like NH3 is going to be considered a weak base. And methylamine, which if you, maybe you watched Breaking Bad, this is methylamine. It's nitrogen-based compounds are going to be weak bases. All right. So those are, that's that. And the last category is non-electrolytes. And this has a 0% dissociation rate. So this is something that's not going to dissolve in water. So it can range from glucose. Glucose does not dissociate in water. It's just a sugar. It'll dissolve, but it's not going to dissociate. That's what we're talking about when we talk about electrolytes. All right. The next class is going to be insoluble salts. So if you take a salt and solubility rule says it's insoluble, if you throw it in water, it's going to be a non-electrolyte because it doesn't dissolve. It doesn't dissociate into its cation, anion species. Are there any questions before we go on to answering these now? All right. So letter A, calcium hydroxide. When you think of hydroxide, you should think of what kind of compound? Base. Now we ask, is this base soluble in water? What do our solubility rules tell us at this point? Hydroxides are generally insoluble, except when they are paired with ammonium, group 1s, and calcium, strontium, barium. So is this going to be soluble or insoluble? If it's soluble hydroxide, does that mean it's strong or a weak? Yeah, so it's going to be a strong electrolyte. The abbreviated SD, strong electrolyte. Now we have something that if you bio majors don't know what this is, then switch majors right now. Glucose, yeah. I'm just kidding, guys. That was just a joke. So glucose is a sugar. A sugar will dissolve in water, but it's not going to dissociate in water, right? It's going to stay in its cyclic structure. So with that, is glucose a strong, weak, or non-electrolyte? Not, right? It'll dissolve, but we're asking, is it going to dissociate? It's not going to dissociate. Does that make sense? So therefore, glucose is a non-electrolyte. Abbreviated NH. a nitrogen-based compound. NH3 ammonia is a weak what? Acid? Weak base, right? So weak bases are categorized as weak electrolytes, believe it or not. So. Am I going too fast, or is this just, am I going too slow, or am I going just right? Like that one story about the bears and stuff. Good, all right. Next one, HBr. You seem like you know everything, okay? So I'm gonna let someone else answer. I'm glad you know everything, Nick. That's really good. But let someone else. Yeah, why is it strong?
Oh, because it was one of the examples we listed for strong.
Yes, it's a strong what though?
Acid.
It's a strong acid. It's one of the 6, and this comes down to memorization, guys, okay? You memorized your 6 strong acids. You'll see HBr on the test and you know that's a strong acid. That means that's a strong electrolyte. So that's how we. Next one, besides Nick, you've exhausted all your answers for the day. So what's the name of this compound? Phosphoric acid. Do y'all agree? It's not phosphorus acid, or is it? It's not. All right. So is phosphoric acid strong or weak electrolyte or a non-electrolyte? Okay. It's a weak electrolyte, and why?
Strong.
That's how we determine if it's a weak electrolyte. Is it one of the 6 strong acids? The answer is no, then it's a weak acid. Therefore, it's a weak electrolyte. All right, 3 more. Copper chloride, or copper 1 chloride. Cuprous chloride. Yeah. You say strong. Why do you say strong? It is a salt. You have a metal and a non-metal. But this is a soluble salt or an insoluble salt, because that'll tell us whether it's a strong electrolyte or a non-electrolyte. All right, let's think about it like this. Are chloride generally soluble? Yes. Yes, right? We think of something like sodium chloride. It's going to be generally soluble because, well, there's a group 1 atom right there as well. So what are the exceptions that are going to make chlorides, bromides, and iodides insoluble? So mercury 1, which is Hg2, 2+. What else? Lead with the +2 charge. What else? Silver. And what else? Copper with a +1. There we go. Lead, mercury, silver. Yeah, I remember those 3, lead, mercury, silver, by just thinking of PMS. P for lead, M for mercury, even though that has an H, and then S for silver, all right? And then copper +1. So PMS and copper 1 are going to make chlorides, bromides, and iodides insoluble. So therefore, if this is insoluble, what would you categorize it as? Yeah, non-electrolyte, right? Because if it's insoluble, when you put it in water, it doesn't dissolve. If it doesn't dissolve, then it has no chance of dissociating. So this is non-electrolyte. Ethanol is next. What are we thinking, guys? Raise your hand if you think it's a strong electrolyte. Raise your hand if you think it's a non-electrolyte. I with pride. That means I want you to 1, 2, 3. Okay, 3. If you think it's a weak electrolyte. All right, we're gonna try this again. I only saw 3 hands. Is it strong? Weak? Oh, wait, no. Okay, non-electrolyte. It's a non-electrolyte. It's an organic compound. When you put it in water, it doesn't dissociate. It'll dissolve, in water, as you see why mixed drinks work, but it's not going to dissociate in water, okay? So this is a non-electrolyte. Remember, it's not a weak acid or it's not a weak base. It's an alcohol. What about that last one there? Strong, right? It's one of those 6 strong acids that we memorized. Therefore, we know it is strong electrolyte. Oops. All right, is there any questions? No questions on strong, weak, or non-electrolyte? It's gonna be a problem on your test, guys. We're all good? Awesome. All right. So we keep going or should, I'm gonna have to leave soon, but do you want to save these till Wednesday? Which one?
Last number 5.
Okay. All right, guys, number 5.
Question 5, before we call it a day. Only did this one because it's like, we can go through it pretty quick, so. All right, so consider the reaction. We all considered it?
Yes.
All right. Thank you for considering it. All right, so identify the following. I want to know what is oxidized, what is reduced, and what is my oxidizing agent and reducing agent. All right, so first step, whenever you think about oxidizing or oxidation, reduction, anything, what should you do?
Balanced.
Or
Should be balanced, right?
plot twist, it is balanced. All right, so it is balanced. There's a certain number maybe you have to add. Yeah. Yeah, the oxidation state or the oxidation number of everything. All right. I know from my advanced knowledge that you don't have to worry about H plus, you don't have to worry about this H2O. All right, let's go through these species. All right. So what is the oxidation state of this oxygen right here? This O4. -2. So oxygen is always -2, except when it's in a peroxide. Then it's -1. Or when it's bonded to a more electronegative atom. All right, so point being, for now, oxygen is -2. All right, what is the oxidation state of this manganese? +7. So how you get that is oxygen is -2, right? So total, you have 4 oxygens, that's -8. And then the total charge has to add up to what? -1, because that's the charge of the ion. So -1 plus X equals -8 plus X equals -1. Add 8 to both sides, you get +7. All right, for this oxygen, what is it? -2. What about for the hydrogen? +1. Hydrogen's always +1 unless it's bonded to what?
Acid, like, or it makes acid though, right? It's like,
Metal. So if it's bonded to a metal, then hydrogen becomes -1. Right. What is my total, or sorry, what is my oxidation number for carbon now? Close. +3. Because again, you can do the same method. What does this one have to add up to, the total charge? 0, complete neutral. So -8 plus 2, this is -6. Then there's 2 carbons, so 2x equals 0. And if you solve for x equals +3. All right, oxygen, y'all know the drill. -2. What about carbon? +4, yeah. There is 2 oxygens, 2 times 2 is 4. So then -4 has to add up to 0, so +4. All right, And what about this last manganese 2+? Yeah, 2+, it's staring at you right in the face. All right, so now that we've gotten all that out of the way, which one of my compounds here, or sorry, not compounds, which one of my or what is getting oxidized? Manganese is going from one oxidation state, +7 to +2,
Yes, lower.
but it's gaining electrons. So if it's gaining electrons, what is that?
Reduced.
It's reduced. So
C is.
the reduced element would be manganese. All right, what is oxidized?
Carbon.
Carbon, because it's going from what oxidation state to what oxidation state?
And lower to higher.
Or it's lower to higher, so +3 to, or I don't know how to, okay, here's how I do it, right? In chemistry, right, when you say something has a +1 charge, you're losing electrons. So if it's going to a higher oxidation number, so from +3 to +4, then you'd say that it's getting more positive, AKA losing more electrons. So if it goes from +3 to +4, we say that the carbon lost electrons and is getting oxidized. So oxidized element, carbon, reduced manganese. All right, what is my oxidizing agent?
It's manganese.
Oxidizing agent is indeed, or can we say it's manganese though? Yeah, remember that you put the entire reactant for when something is an oxidizing agent or a reducing agent. This is also important. Oxidizing and reducing agents can only be reactants. In any sort of scenario, like you shouldn't put like carbon dioxide as your oxidizing or reducing agent ever. It's only reactants. So your oxidizing agent is the one that is reduced, so it's manganese. Mn, or the total compound MnO4-. All right, reducing agent.
Would be C for carbon.
What did I just say?
Well, for CO2.
Wait, you said you did. Double brown.
That's something about reactants.
Did the H2C2O.
Yeah, H2C2O4. So that is our reducing agent. But what can my, what is the only side of my chemical equation I should be looking at for oxidizing reducing agent, Nick? The left, or the reactants. Only look at reactants when you're looking at oxidizing reducing agent. Then remember that agent means it does the opposite. So oxidizing agent gets reduced, reducing agent gets oxidized. And with that, speaking of oxidation, that is all we got for today. Next session, Wednesday, 12 to 1, pull up. And we'll go through problem 6, and then we'll have some more fun problems for y'all.
How did y'all like the little time to work on it yourself and then go over those questions? Okay, maybe we'll keep doing that. If you want an extra copy, so maybe you can work on it later by yourself. Then I'll leave them right here, okay? Yeah.
I'm gonna have
I looked at the last one. The last one. Well, I only wrote the.
Never concepts, then you never have